Hi, everyone. Welcome to discussion 7 on asymptotics and BSTs or binary search trees. Announcements, the ones applicable by the time this is released on Wednesday. Lab 7 is due on Friday, March 5th. Project 2 checkpoint is due on Friday, March 12th. Homework 2 is due on Monday, March 15th. And last but not least, start Project 2. Get Lit is a beast. You want to start it ASAP and know what your questions are, so you can take them to office hours and stuff. So let's just all get started on Get Lit. Now for some content review. First, let's talk about abstract data types. Abstract data types are data structures where we know what they do, but not how. And they're usually represented as like interfaces or abstract classes in Java. And so an abstract data type is not like a thing in code per se, so much as it is an idea that programmers all agree upon. And so, for example, the list abstract data type, we can imagine that all lists will have some set of operations such as, and like characteristics such as you can get an item at a specific index, you could add items, you could remove items, and the items are going to be in order. And so that is what a list should do. It should be in order. It should have a way of like getting specific indices. It should have a way of iterating through it, et cetera, et cetera, et cetera. But we don't really care how they do it under the hood. The list is an abstract data type, and it could maybe like manifest itself, I guess, in specific implementations such as array list or linked list, but the abstract data type is just list. Similarly, the map abstract data type basically requires that we can map keys to values. And so if we put in, let's say, a key value pair, like, I don't know, Allison 20, because that's how old I am. Like if we were matching names to ages, and we should be able to put those into our map data structure. And then if I were to say things like get Allison, it should return 20. It's so weird, like hearing my own name, saying my own name. Anyways, and so like basically the idea is that a map maps keys to values. And so once again, that is what a map should do. How the map does that, whether under the hood it's a hash map or tree map or whatever, we don't really care. They all are implementations of this abstract data type map. Similarly, a set abstract data type is an unordered collection of items that does not allow duplicates. And so we know that with the set, we should be able to add things, and it doesn't matter how many times we add it, it'll only end up in the set once. We should be able to find out if something is in the set, etc. And there are all these things that as programmers, we expect sets to be able to do. How they actually do that is up to like the specific implementation. So hash set or tree set are specific implementations of the set abstract data type. We also have the queue ADT, which basically says if we push things to the front of the queue, we'll eventually be able to pop them off the back of the queue. And so things come in order, and basically the first thing to come in will be the first thing to come out. Or in other words, we all like wait in line and they get popped off in their turn. On the other hand, a stack is basically you push things onto the top and you also pop them off of the top. And so this is like the last thing that you just pushed onto the stack will be the first thing that you pop off. And so those are the queue and stack ADTs. And this is just this concept that really helps us as like programmers sort of be on the same page as each other and understand like what operations we expect our data structures to be able to do. And so a binary search tree is a specific data structure now. So we're moving on from ADTs. And a binary search tree is a specific data structure that allows us to quickly access elements in sorted order. And they have several important properties. Each node in a BST is a root of a smaller BST. So for example, where this is a whole BST, this node is also the root of another sub BST. And this is also the root of another BST. And technically, even the leaf is the root of a smaller BST. It's just one with no other elements besides this like leaf. And so every node to the left of a root has a value lesser than that of the root. And so, for example, if this was 5 and we were doing like integers, we would know that every element in this whole left branch of the tree must be less than 5. And similarly, everything on the right must be greater. And that is like the 3 important properties of a BST. And BSTs can be bushy or spindly. And so when you have a bushy BST, it basically means you look like this, right? And so the height is limited to log n. Whereas if you have a spindly BST, it actually looks more like a linked list. And so you have linear time operations. And so those are our little intro to BSTs. For BST insertion, items are always inserted as leaves. And so, for example, if we wanted to insert 2 into this BST, we would start at the root and we would go, okay, 2 is less than 5, so go to the left. 2 is less than 3, so go to the left. 2 is greater than 1, so go to the right. And whoops, there's nothing there, so we'll insert it now as a leaf. And so we would put 2 in. And so that's what's happening here on the right. We've inserted 2. For the deletion, we use a method called hybrid deletion. And so there are several cases to consider. But basically, the premise behind hybrid deletion is that we want to keep these properties of our BST, right? That the left is always less than and the right is always greater than. And so in one case, if we're deleting a leaf, it is pretty easy, right? We just delete the leaf. And so if we wanted to delete 2 here, we would simply, oops, erase it, and it's like nothing happened. But what happens if, let's say, a node has only 1 child? Well, then again, we can just take the node we're deleting with only 1 child and take that child and replace it. And so 2 actually moves to where 1 previously was. And then we act as if the child was deleted in a recursive pattern until we hit a leaf. And so 2 will move right here. And finally, we consider the case where a node has 2 children. And so here, if we call delete on 5, what we would do is we would either pick the leftmost node in the right subtree or the rightmost node in the left subtree. And so basically, if we look at the left subtree beneath 5, we would see the rightmost node is 4. And so, for example, we could stick 4 up here, and we'll see that this still keeps our BST like properties, right? Because everything to the right is greater than 4 and everything to the left is less than 4. And so this is a perfectly valid BST. On the other hand, we could also have maybe left 4 there and put in the leftmost node of the right subtree. And so again, the right subtree for 5, or the node we're deleting, is this one. And the leftmost node here, or the node most this way, if you don't know your left and right, sometimes I struggle with that. The leftmost would be 6. And so we could also have maybe deleted 5 and put 6 where 5 used to be. And now the BST would look like this. And we will see once again, this is another valid way of doing it because this is a valid BST. Everything to the left of 6 is less than 6, and everything to the right of 6 is greater than 6. And so either way works. And if we ask you to do this on a test, of course, we would specify which one you would go with. And lastly, I want to go over some important points in asymptotics. The first being that asymptotic analysis is only valid on very large inputs, and comparisons between runtimes is only useful when comparing inputs on different orders of magnitude. And so that would be things like, for example, just making a little chart, right? And saying if I have the get method for my array deck and the get method for my linked list deck, and I want to know which one is faster, the comparison is only going to be useful if you try it, for example, first with like n equals 1,000, and then n equals 10,000, and then n equals like 100,000, or let's do 50,000. It seems more reasonable, perhaps. And so the idea would be here that let's say at n equals 1,000, get takes 1 second, and linked list deck takes 0.5 seconds, right? And you might go, oh my God, linked list deck is hands down better. Like it's just so much better. But then you realize that at n equals 10,000, get with the array deck also only takes 1 deck. And at n equals 50,000, get with the array deck also only takes 1 second. Whereas get with the linked list deck, let's say, for example, scales with the size of the input, which is actually not supposed to do if you did the project right. But let's say you implemented it in some way where with n equals 1,000, it only takes 0.5 seconds. But as soon as you do n equals 10,000, now it takes 5 seconds. And then you say n equals 50,000, and now n takes like 10 seconds. And so you're realizing, wait a minute, my array deck implementation is actually asymptotically better than my linked list deck. And so this is the whole idea where you have to compare inputs with different orders of magnitude so you can get an idea of how it scales, not just how it performs for some like given input, right? And so that is that. The other thing is that there are some common ideas we see in asymptotic analysis, and they can definitely be useful, right? If you have this like set of knowledge that you can rely on, or like gut instincts, but you have to be careful because rules like, oh, trees are always 2 to the n because you're growing and you're doubling every level, or nested for loops always give you n squared time because the first loop is n and the second loop is n also. Those things can easily lead you astray. And so you really want to be careful when you're doing your analysis, not just to like gloss over little details and be like, oh, I know this, I've seen this before. And finally, doing problems graphically can be helpful if you're a visual learner. So for example, if we had a for loop like this, where it starts at I equals 0 and it goes up to I equals n, and then another for loop where it starts at 0 and it goes up to the value of I for that iteration, this might be a little bit hard to analyze on your own, but one way you could do it is by going graphically. And so here we have the I axis, which ranges from 0 to n. And what we see is for j equals 0, or for when I equals 0, I is going to go, or j is going to go from 0 to, this graph is actually backwards, I'm realizing. It should definitely be like this. Anyways, when I equals 0, j is 0. When I equals n over 2, for example, j is going up to n over 2. And when I equals n, j is going all the way up to n. And so we see the work done is basically this area in the triangle here. And the area of a triangle, let's do some geometry, it's 1/2 n squared if n was the side and it was an equilateral triangle. Not equilateral, whatever the heck this shape is, a square divided in half, right? We can also just think of the area of a square divided in half. And we're going to see it's 1/2 n squared. And remember, in asymptotics, we always drop constant factors. So really, this leads us to n squared runtime. And so that's a way of analyzing things graphically. Sorry, this triangle is backwards. Note to self, fix this. But yeah, that is some graphical asymptotic analysis. And now we're going to move on to the worksheet. So the first question is ADT matchmaking. Match each task to the correct ADT for the job. So I want you to take a moment and think about all of these and then come back to me once you have really thought hard about it. I'll give you a second. Woohoo, and you're back. So the first one, you want to keep track of all the unique users who have logged onto your system. And so I'm thinking about this. And the first thing I notice is that you want to keep track of unique users, right? So that sort of implies to me that even if a user logs on to your system like 10 times, they should probably only be in your little data structure once because we only care about how many individual users ended up visiting. And so this to me immediately ticks off, maybe we're looking at a set. And the more I look at this, a set does seem to make sense, right? We don't really care about the order, it seems. Nothing about this implies that we care about the order. We don't want duplicates, and it doesn't really make sense to use a map or anything because I don't know what the key value pairs would be here. And a queue, again, I don't really know why we would want to use a queue because there's no sort of like pushing new things on, or I guess you are adding new things as they log on, but I don't see where you're popping things off. And so a queue doesn't make sense. And a set makes more sense than a list here because we want unique items, and sets really naturally support unique items. Okay, cool. You are creating a version control system and want to associate each file name with the blob. Sound familiar? I hope it does, because you've started project 2, right? Anyways, we're making a version control system. We want to associate each file name with a blob. Immediately, this to me feels like a appropriate task for a map, because we want to map a key value pair where the key would be the file name and the value would be the blob. And so that seems to check out for me. And once again, I don't think it would be a list, because to do that with a list, you'd have to like have some sort of weird element in your list that like carries both the file name and a blob. And it doesn't really seem like we care about the order or anything like that. And similarly with the queue, it just doesn't seem natural to try to like push these onto a queue and then like you're not really getting these by popping them off in a particular order. Instead, you want to be able to access them by the file name rather than getting just like the last or the first thing that was pushed in there popped off. And so a map definitely makes sense here. Next, we are running a server and want to service clients in the order they arrive. The last two options up are list and queue. And I think about it and I'm like, okay, maybe we could put them on a list, right? Like we have some sort of list representation, and then as clients arrive, we like put them in the list and we're like, oh, okay, look at, we have all these clients. And then as we service them, I guess we would maybe remove them from the list and then like go along and keep track of what we've removed. And it seems a little complicated. Whereas a queue really naturally supports this, right? Because as clients arrive, we just push them onto the queue and they'll get popped off in the correct order that they came in, because a queue supports first in, first out. And so I think a queue really naturally fits here. And that leaves list for the last one, but let's take a moment to actually see why this works. We have a lot of books at our library and we want our website to display them in some sorted order. We have multiple copies of some books, but we want each listing to be separate. So we can imagine maybe like if we have, I don't know, 10 copies of like, why can't I think of a book? I've read books before, I promise. We have 10 copies of Catcher in the Rye, and we want them all to be separate listings because, you know, 10 different people could come check them out and they might all be in different places or like whatever. And so we want them to all be separate, which means we do support duplicates. The other thing is that we want them to be in a sorted order, and list is the only like naturally sorted collection here. And so all of this supports using a list in this scenario. Woohoo! That was problem 1. Next, AmSpeed. Give the worst and best case running times in theta notation in terms of m and n. And so m and n are 2 variables defined here. Assume that the function come on runs in theta 1 time or constant time and returns a Boolean. And so once again, I will give you a moment to pause and do the problem on your own if you would like, and then we'll go over it in detail together. Ooh, okay, and now we're back. I hope you had a delicious time working on this by yourself. We are going to go over it together now. So we want the worst and best case running times for this function. I noticed that there's an outer for loop that is incremented by adding 1 and it goes up to n. And I see that there's an inner for loop where it starts at 1. We run until j is equal to some value m, or as long as it's less than m, I guess technically. And instead of incrementing right here in the for loop, we actually increment in the body of this like for loop statement. And there are 2 cases. Either we increment by adding 1, or we increment by multiplying j by 2. And we see that this inner loop is basically going to go until that happens. And so taking a moment to pause, is the best case if come on returns true and we're here, or is the best case that we end up in the second statement? So think about it. I think the best case would be that we always hit the second statement, right? Because the faster j grows, basically the faster we get to exit from this for loop, or in other words, the less time we have to spend in this inner for loop. Because if j, let's say m was, I don't know, 32, and j starts at 1. If j increments by 1 every time, how many times do we do this inner for loop? Well, we do it once, then the second time, then the third time, then the fourth time, and so j, these are the values of j. We would go all the way until j equals 32, which would take adding 1 32 times. What if we hit the second case every time? Well, then j starts at 1, then it's 2, then it's 4, 8, 16, 32. And so that only takes 5 iterations of this inner for loop, right? And so that is much faster than if we had to add 1 every time and do this for loop 32 times. And that's just an example where m equals 32. And so I see that the best case is if we always hit this. So why don't we start doing that best case analysis? Well, in the best case then, what we see is that the inner loop or the outer loop starts at 0. And so I'm doing this sort of like visual representation, if you like that. And so this is the I-axis, starting from 0 and going up to n. And I would see that for every value of I, how much work will happen in the inner loop? Well, independent of I, j is always going to be log m. And this would be because j starts as some initial value 1, right? Oops. And in the best case, for every iteration, we multiply this number, or j, by 2. And every iteration this happens. And so if there were x iterations, we would end up with a value that is 2 to the x, because we start at 1 and we multiply by 2 x times. And if you recall, 2 to the x is just the same thing as multiplying by 2 x times. And we want to know, when does this value reach m? Because that's when we'll terminate. So in other words, once we've hit x iterations, we're going to reach the point where j is equal to m and we terminate the loop. So x is the number of iterations that will happen. And we can solve this just like any other math problem. And we will see that there's the relationship that when you have 2 to the x equals m, this means x equals log base 2 of m. And this is just a math rule that you will have to remember. But basically, we need log base 2m operations or iterations in this inner for loop. And so we're going to have log m work happening every time, right? This is the j-axis. And so log m work happens for all values of I, which means that the total work done is this area in the graph, or in other words, n log m. The other way I think about it is just like whatever's in the inner loop happens outer loop many times. Well, the inner loop takes log m work and the outer loop takes n, so it's n log m. And that is the best case scenario. What about in the worst case? Well, the outer loop still happens n times, but what happens in the inner loop? How many times does the inner loop happen? Well, in the worst case, we're adding 1 every time, which means if we start at 1 and we want to add 1 until we reach m, well, that's pretty much m additions, right? Technically, I guess like m minus 1, but we don't really care about these like little constant -1 factors. So we would say that the inner loop has to happen m times. And once again, if we drew our little visual representation, we would see that on the I-axis and the j-axis, regardless of the value of I, the inner loop is going to happen m times. And so we get the work is n times m. In other words, the outer loop happens n times, the inner loop happens m times, and so that is n times m. And this is the best case on the left and the worst case on the right. And that is problem 2. Congrats, you did it. Finally, we're going to move on to problem 3. This covers some recursive problems with asymptotic analysis. And so these are really not that fundamentally different from the other like iterative problems we've seen. And the only difference is that, especially with recursion, it can be helpful to draw a recursive tree in which each layer of the tree is just representing the work done there. And so we will go through and see what that really looks like. In this first problem, 3a, we just want to know what is the runtime in terms of n, where n is an input to our function, curse. And we see that curse takes in, oh, it looks like this is a typo. It doesn't return an int array, it returns an int. And so we say if n is less than or equal to 0, we will return 0. Otherwise, we're just going to return n plus curse of n minus 1. Very cool. And so we see that at the top level, we will do a constant amount of work, right? We just do an addition. The real question is, how much or how many levels are there, right? And so you can imagine that curse of n will take constant work to do an addition. And then what happens below? Well, we make one call to curse of n minus 1. And we make a call to curse of n minus 2. And a call all the way down until we finally reach curse of 0, at which point we terminate. And so this is our recursive tree. Here it really looks more like, I guess, a linkless or a spindly tree, right? Because our recursive calls are not branching. But we see that the depth is overall n. And at each level, we do constant work or just one addition. And so the work done is the depth of the tree multiplied by the work done at each layer. And here the work done at each layer is constant. And so n times 1 equals n. And so the total work done here is n, or linear. Moving on to 3b. We have a BST, and the full problem statement actually says we can assume that the BST is perfectly bushy, or in other words, it looks like this and not like a linkless. And we want to know what is the runtime in terms of n, the number of nodes in the tree. And so we're going to take a closer look at this. We see that we have a BST, and it looks like we can assume our BST objects have a left or like a left subtree, a right subtree, and as a key, which is the value of that node. And so, for example, I guess zooming in on this, if our BST looked something like this, we would see that the left value for this node 5 points to 3, the right for this node 5 points to 6, and the key would be 5 here. So that's the baseline for this problem. And now I'm going to give you a moment to do the asymptotic analysis by yourself if you want, and then we'll come together and do it. Okay, so let's jump right in and see what's happening here. Basically, what I'm noticing is we're going to start by calling find on, let's say, some tree, who knows, and you're looking for some key, who knows what they are. And we're either going to hit one of these 4 cases and only one. If it's null, we'll exit out and nothing happens. If it's we found the key already, we also exit out, cool. And the interesting or like recursive cases are when you haven't yet found the key. And the key thing to notice is that we're only going to execute one of these like child recursive cases, right? Either the key we're looking for is less than the current node's key, in which case we'll move to the left, or it is greater than it, in which case we'll move to the right. The equal case already being covered up here. And so we're not going to execute both of these recursive calls. We only ever execute one. But we know that regardless, we're moving one layer lower. So we could say maybe tree with one less layer is the recursive call. Whether it's the left or right, we don't really know. But we know that whatever recursive call we make, it's going to be one layer beneath it. In other words, if our tree looked something like this, blah, 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 if the initial call started here, we're going to call find on either its left child or its right subchild, or we could exit out immediately if we already found the key. but these are one layer shorter than its parent. And once we're in these cases, again, we're going to call the find subroutine on one of its shorter children in the worst case where we haven't found it yet. And so this happens over and over and over again. And so each time we're going to be finding with a tree 2 less layers than this original tree passed in, etc. And in the worst case, we'll keep going all the way until we reach the bottom or the leaves, at which point the BST is null because the leaf has null children. And so we would reach all the way down there, blah, 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 blah. And so basically, tree with like 0 layers, or in other words, how many less layers does it have than the original one? Well, that's log n, because the height of the tree in a perfectly bushy BST, which we were guaranteed, is log n. And so if we originally started with some tree and now we're at 0, or in other words, the leaves, this tree has log n less layers than the original. And so the question is, how much work or how long does it take for us to get from this top recursive case to the bottom recursive case? Or in other words, what is the depth of our recursive tree here? Well, it's log n, right? We start at the first tree, then we go down to a subtree with 1 less layer, then 2 less layers, all the way until we reach the leaf. And that is limited by the height of our tree, which in this case is log n. And so the depth of our tree is log n. What about how much work happens at each layer? Well, basically, it's a constant amount of work, right? It doesn't depend on the size of our tree, because all we're doing is like a comparison with the current node, and then like picking one of these cases and executing them. And that doesn't scale with the size of the tree, right? Checking if it's null, checking if it's equal to the current node is a constant time operation. And so overall, we see each layer has constant work, and there are log n layers. And so once again, with recursive asymptotics, it's easy to think just what is the depth multiplied by the number of work at each layer. And so how many layers times work at each layer, in this case, is log n times constant, or 1, which is just log n. And so we see the find operation for a BST is log n. Woohoo, you maybe already knew that if you were caught up on lecture, but now we've actually proved it to ourselves and seen why. Last but not least, 3C, recurse with asymptotics. Can you find a runtime bound for the code below? And we can assume that the system.arrayCopy method takes n time, or linear time, where n is the size of the input array. And we see that is named R here. And so let's walk through what this method is doing together, and then you can do the analysis on your own. So we're given this array, and we say, if the length is less than or equal to 1, we're going to outprint U1. Otherwise, we will say the new length is equal to the current array's length divided by 2. And so, for example, if the input array was originally of length n, we're now saying new len is n over 2. And we're going to declare 2 new arrays of size new len, which means they are 2 arrays, each of half the size of the original. And we will call one of them first half and one of them second half. And so I'm just sort of labeling what's going on. And then we say system.arrayCopy, our input are from starting at 0 into first half starting at 0, and we're going to copy new length elements. And so it's okay if you don't know the arguments to system.arrayCopy off the top of your head, but that is what they are. It's basically the source, where to start in the source, so that's here, then the destination and where to start in the destination, and how many elements you want to copy. And so here we're copying n over 2 elements, or in other words, the full size of first half. And so we can imagine if, let's say, R originally looked like this, we're basically copying all of that to first half. We also say array copy starting at new length, so now starting at this point n over 2, And we're going to copy that into second half, starting at 0. And we're going to copy new length amount of items. And so that does this. Cool. And then finally, we call silly on first half and second half. And so we are making a recursive call, 2 of them, to each of our subarrays. So I will give you a moment to do some analysis on how this actually runs, and then we will go over it together. And now you're back. Hopefully you've had the bestest time ever. And just as before, I'm going to start us off by drawing the recursive tree. So I'll maybe move this to the side because it's less relevant right now, but we'll keep it for reference. But we want to look at the recursive tree. And so you would see that originally we start with a call of silly to with this array of length n. And so I'm actually just going to say like r len n, and that's very cool. We see that the subroutines, we're going to actually end up calling silly with an array of length n over 2 and another array of length n over 2. And each of these are going to give silly n over 4, n over 4, n over 4, n over 4. I'm dropping a lot of the words because I don't feel like rewriting them, and so on and so forth. And this happens, and it stops finally when we reach the case where it's length 1, right? And so all of these recursive cases branching out in our recursive tree will stop when we're calling silly of 1. I don't know why I keep writing sil. So that is the depth. And so taking a moment, let's think about how many layers are in this tree, right? We start at n, and basically we're halving it every time until we reach 1. How many times do we have to have it? In other words, if we start at n, and we multiply by 1/2 at every layer, and there are x layers, so basically we're repeatedly having this at every layer, how many layers will it take until we reach n? In other words, n over 2 to the x equals 1. What is x? Or in other words, what is the number of layers or recursive calls? Well, in this scenario, doing some math, this also works out to be n equals 2 to the x, which means x is log base 2 of n. And so this is just some mathy math, but that is what we work out to. So the depth of our tree is log n. What about the work that happens at every layer? Well, at the top layer, recall that really doing this like division doesn't really matter based off the input size of the array. This is constant no matter the input size of the array. This is constant. Oh, but look at this. The array copy takes linear time where n is the size of the input array. And so here, basically these calls depend on the input. And so it's not just constant work at each layer. Specifically, it's linear. And so the first call is going to take how much time? Well, if we were starting looking at this case, we see that we call array copy on an array of size n over 2, and we do it again with another one of size n over 2. So in other words, at the top layer, we do n over 2 plus n over 2 work, or n work. Very cool. What about at the next layer? Well, now we're calling silly with an array of length n over 2. What's going to happen specifically in this call? Well, we'll do array copy on the first half and the second halves, which are each half of this input. And so we do n over 4 work in each call, or in other words, this is n over 4 plus n over 4, which is n over 2. And what about in this call? Well, this one is identical to the one we just did on the left, which means this call also does total n over 2 work. Then this whole layer sums out to be n work. And so actually I'm going to try to be a little cleaner right now. So give me a moment. This whole, so as we recall, we said the first layer does n work total. The second layer also does n work total because we're doing n over 4 plus n over 4 and n over 4 plus n over 4. Or in other words, really a call to silly with length n over 2 does n over 2 work. Because we're overall array copying the whole length of the input array. And what about the next level? Well, now we're calling silly with n over 4, which takes n over 4 work. And we do that 4 times, which means this is n. And blah, 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 until we reach the very bottom. And we see this would also be n, because even though there's constant amount of, or not constant, but rather there's one work being done in a call to silly of array length 1, the width of this, or the amount of actual calls, is going to be n, right? And so this is n work. Wow, interesting. So each layer has n work. And as we said earlier, there are log n layers. And so the total work done is the depth, or the number of layers, multiplied by the work done at each layer, which means this is n log n. And that is super cool. So hopefully this has given you some idea into how recursion and asymptotic analysis fit together. The last problem, have you ever went fast, is actually covered in one of Anjali's videos. So I'm going to go ahead and link that in the description below. It is extra, but it is super fun and super worth it if you want to go ahead and do it. But I hope you have a great day, and please make sure to take care of yourself, drink some water, get some sleep, and enjoy your life. Peace out.